Hi, this is Kate, and we're solving linear systems by substitution. Dear Uncle Lester, thank you for the birthday card. My Uncle Lester is so thoughtful. Whenever I see an envelope in the mailbox from Uncle Lester, I know it will bring a smile to my face. You are the best Uncle Lester in the world. Love, Kate. Now, sometimes when you have a birthday or a celebration, when more than one person gives you a gift, you have to write a lot of thank you notes. And you end up doing something like this. Dear Aunt Sally, thank you for the birthday card. My Aunt Sally is so thoughtful. Whenever I see an envelope in the mailbox from Aunt Sally, I know it will bring a smile to my face. You are the best Aunt Sally in the world. If you'll notice, it's exactly the same note with the name Uncle Lester changed to Aunt Sally. So fess up, have you ever done this before? If you said no, you're a better person than me. Normally, thank you notes are handwritten, but if you're using a word processor, there's a way to find every occurrence of a specific word and substitute in a different word or phrase. Do you know what this is called on a word processor? It's normally called a find and replace. You find every existence of a word or a phrase and you replace it with something else. In our example, we replaced all the occurrences of Uncle Lester with Aunt Sally. So what in the world does this have to do with math, you are wondering? Well, we're still solving systems of linear equations. We want to find two different numbers, x and y, that make both of these equations true at the same time. In a previous lesson, we saw how we could graph both of these lines. All the xy pairs that make the blue equation true fall on the blue line, and all the xy pairs that make the red equation true are somewhere on the red line. So the xy pair that makes both the equations true is the point that lies on both the blue line and the red line, the point of intersection. This system is a little bit difficult to solve by graphing because you'll notice that point of intersection does not fall at an integer. The answer is a fraction that's in between two whole numbers. We do have a way to solve these that doesn't require graphing, that's purely algebraic. And it has a lot to do with the find and replace function on a word processor. I know that in this system, y equals x minus 1. The second equation has a y in it. So what we can do is replace that y. So I write out 7x plus 3 times something equals 12. I can replace the y with what it's equal to. It's equal to x minus 1. Now check it out. We just have an equation with one letter in it. That new equation we wrote only has x's in it. So you could solve this for x. Why don't you go ahead and do that now? You should have gotten 1.5. First we'll distribute the 3, combine the 7x and the 3x, add 3 to both sides, and then divide both sides by 10. 15 divided by 10 is 1.5, or if you wrote it as 3 halves as a reduced fraction, that would be correct also. So what do we have so far? We know that the x-coordinate of this point we just found out is 1.5. However, the answer to this question has two parts, the x value and the y value, that work together to make both of the equations true. Well, we know that x is 1.5. So in both of these equations, I'll replace the x with 1.5. We could use either equation to solve for y, but one of them is a lot easier to work with than the other. Which equation looks like it would be easier to use to find the y coordinate, the red or the blue equation? In this case, I would definitely pick blue, because all we need to do is subtract 1 from 1.5 to get the y coordinate. The solution to this system is when x is 1.5 and y is 0.5. Let's try another. In this system, x equals -10 and y minus 5 equals 6x. We want to replace the x in the second equation with what it's equal to. Look at the choices carefully and please choose the helpful and correct substitution we could make. If we replace the x in the second equation with negative 10, we get y minus 5 equals 6 times negative 10, just replacing the x with what it's equal to. Now you can use this to find the y coordinate of the solution. Please do that now. The y coordinate of the solution is negative 55. First we'll multiply 6 by negative 10, and then add 5 to both sides. So put it all together. What is the solution to the system, the xy pair, that makes both equations true? Both equations are true when x is negative 10 and y is negative 55. We want to solve this system. We want to find a pair of numbers x and y where 2 times y plus 6 times x equals 5, and y minus 2 times x equals 1. This is a little bit harder than the previous examples. In the last one we looked at, we already had x equal to something, so we could just replace the x in the other equation with negative 10. In the example before that, we had y equal to something, so we could just replace the y in the second equation with what it was equivalent to, x minus 1. However, in this problem, we don't have x equals something or y equals something. We have to do a little bit of work first to isolate one of the variables. The easiest thing to do is to take that second equation, the orange one, and get the y by itself. So what would it look like if you isolated y in the second equation? In order to get y by itself, you would need to add 2x to both sides. Now that we've rewritten the second equation as y equals 2x plus 1, we can replace the y in the first equation with 2x plus 1. Which choice represents the appropriate substitution? Choice A is correct. In choice A, we replaced the y in the first equation with what it was equal to, 2x plus 1. Now that we just have an equation with one letter in it, with x's in it, you can use that to solve for x. Go ahead and do that now. The solution to this equation is x equals 3/10 or 0.3. First we'll distribute the 2, and then combine together the 4x and the 6x. Subtract 2 from both sides, and then divide by 10. Okay, so we know the x-coordinate is 0.3. Please substitute 0.3 back in for x into either equation to find the y-coordinate of the solution. I'd recommend plugging it into the second equation. The y-coordinate of the solution is 1.6. If I substitute in 0.3 for x in the second equation, 2 times 0.3 is 0.6, and 0.6 plus 1 is 1.6. So we think our solution is 0.3, 1.6. We should go back and check that in that first more complicated equation, just to double check we didn't mess anything up. So we'll sub in the 1.6 for y and the 0.3 for x, multiply these things, check that they add up to 5, and they do. This is Kate, and you've been solving linear systems by substitution.